All right, I think we are live. Hey everyone, thank you so much for joining us for the episode 4 of Lakehouse Chronicles with Apache Hoodie. We will get started in a moment. We'll give it a minute or so for people who are just joining in. Let us know where are you joining in from today. If you're already using Hoodie for your Lakehouse-based workloads, or if you have any other questions or suggestions, feel free to bring it up. We also have different series that we usually run as part of the community edition, which is the Hoodie Community Series. Uh, so if you have any interesting implementations or any kind of implementation that you have already done using Apache Hoodie in your organization, reach out to us and we'd be happy to host a session and bring out all the things that you have been doing in your organization to our community. All right. I think we are kind of, at the top of the hour to get started. So, let's dive right in. So, a little bit of introduction, in terms of the series overall, is that, with this brand new series, which is the Lakehouse Chronicles with Apache Hoodie, we aim to bring exciting talks and content for the Hoodie community. We usually have discussions on critical topics, go over architecture internals, do some show and tell on how to get started with Hoodie. Uh, Even things like interviews with PMC members. That's what we are thinking of doing, so that we can get your questions answered and also talk about some of the interesting things that are coming up in the Hoodie project. Hoodie 1.0 is something super interesting as well. So, feel free to check out the beta version. We are very close to the finish line, and, hopefully, we will have more people get access to that. So, overall, with this series, the idea is to make things easier for developers and users to get started and use Hoodie in their workload. So, irrespective of if you're an already experienced Hoodie user or contributor, or someone who is completely new to this entire space of Lakehouse, and specifically Hoodie, you should be able to find a lot of beneficial content over here. We will also have a recorded version for each of this session, and that way you are free to basically explore them afterwards, in case you cannot join the live ones. So today I will be your host and speaker. My name is Dipankar. I'm currently a staff developer advocate here at OneHouse.ai, and I contribute and support open source projects at OneHouse, specifically things like Apache Hoodie, Apache Xtable. I have also been involved with this Lakehouse ecosystem for a while now. I have worked with projects like Apache Iceberg in the past, Apache Arrow, of course. I'm also very much active in my social. So if you have any questions regarding the session or anything in and around lake houses, feel free to drop me a message, and I'd be happy to interact. So to get started with the session, let's kind of start with the problem statement, right? Everything that we do has a problem statement, I guess. So one important aspect of the current Lakehouse platform is that they are predominantly distributed in nature, right? And that kind of makes sense, right? They're designed to handle this large scale, complex data workloads, right? So whether it's that Lakehouse platform, open Lakehouse platform like Hoodie, or something like Iceberg or Delta, this typically requires setting up clusters, with Spark, JVM, and you know what, there are some downstream dependencies as well. There are some storage system based dependencies, like for example with Hadoop, S3, if you're using something like S3 based buckets for a data lake. So those configuration and dependencies also come into the picture. But not all Hoodie users may need to rely on these dependencies, right? So we'll go into the problem a little bit more deeper. But just to summarize, if you take this simple example that I have put it out, right? Here we are obviously the prerequisite to run something like a PySpark program on top of something like Hoodie or Iceberg or any kind of table format. It requires you to have this Hadoop-based dependencies, like AWS-based dependencies. Then there is things like you need to have Spark installed, JVM installed, and that can be cumbersome, right? So going to the problem a little bit more deeper in our next slide, not on the other end of the spectrum, there is this growing set of users. The persona of these users are mostly maybe data analysts, data scientists, or even data engineers, right? Who are basically dealing with kind of this Python-based workloads or Rust-based workload. They need to either query data directly from this Lakehouse format, and the reasons can be multifaceted, right? It can be ad hoc queries. building analytical apps, or data science and machine learning based use cases, which is one of the common reasons that you typically like to use something like a Lakehouse format and access data directly from the format to do your analysis and inferences and training and stuff. So these users typically rely on like this Python or Raspberry single node tools like DuckDB, Daft, Polars, Pandas, Data Fusion, along with visualization based libraries like Streamlit, Plotly, and for such use cases, they don't always need to go through the cumbersome process of setting up the infrastructure itself, right? For example, for data science and machine learning based applications, they often need frequent access to diverse data sets, right? For exploratory data analysis, model training, model inferences, and those kind of workloads. Um, so having the direct access to these Hudi data sets for these use cases, one is you get all the benefit of these table formats, right? They're open in nature, so really, interacts with different kind of system, but also like things like schema enforcement, schema evolution, right? Ability to like, change a certain particular feature, or modify a certain feature within that particular table, or do things like, time travel for that matter, and go back to a particular version of the table and run your model on that particular version of data. So these are the kind of thing that you'd like to do, right? When you're doing this kind of analysis and kind of like data science roles. So because if you have worked in this kind of, if you kind of have worked in this kind of role in the past, or you have been a data engineer who have been providing data sets to this set of users, it kind of takes a lot of time to get to the point where you kind of request a ticket for getting the data set versus how it would have been feasible for them to like just go and access the data set directly from the Lakehouse table formats, right? So traditionally, accessing these Hudi tables, it would involve configuring like Java, Hadoop, Spark, and other related dependency. Of course, that's what you need for a more distributed setting. So this is what Hudi-rs kind of tackles and makes it easier for these kind of people in their jobs who are trying to rely on Python or Rust-based ecosystem workloads. And that's what we are going to discuss a little bit more. So introducing Hudi-rs, it's a Rust native library for the Hudi Lakehouse platform with Python bindings. That means you also have the Python API. So that allows you to access Hudi tables directly from your cloud storages like S3 Bucket, ADLS, or GCS using pure Python or Rust, right? So this opens up an exciting new world where users can really read all of this like Hudi tables using non-JVM based compute engine, right? And we talked about this dependencies and like kind of the necessary the kind of necessary packages and stuff that you require. Now, before we go and understand how to use Hudi-rs today in this kind of brief presentation, let's take a moment to understand its internal first, which will provide a little bit more context for its integration with the downstream libraries as well. And that will help us, we'll also see that in action in one of our presentation as well. So under the hood, Hudi-rs, it basically uses Apache Arrow, which makes it easily compatible with other Arrow native libraries and tools. Now, if you haven't heard of Apache Arrow, you probably should. Its standard definition is that it's an in-memory columnar format. So basically, it's a data representation that can be utilized by any processing engine, and it's in memory. So Arrow is neither a storage nor an execution engine. It basically serves as a language agnostic standard, if you may, for in-memory processing and data transfer. So this means that when two different disparate systems, they speak Arrow, there is no need for additional serialization and deserialization of the data during this transfer process, right? And that enables interoperability between these different languages or systems and help you reduce that serialization and deserialization cost. Because to be honest, most of the time that you spend in this particular like data transport process or data transfer process is this particular SERDE process, right? So as you can see in this image, Hudi-rs, it scans the record from a Hudi table that is sitting in a local file system or any kind of cloud object store like S3, and it puts them out into Arrow record batches. Now, what is an Arrow record batch? A record batch is basically a collection of equal length arrays that conform to a particular schema. Okay, so it is a table-like data structure, kind of similarity wise. Essentially a sequence of field where each field is a contiguous arrow array. So that's what you need to do. And once this particular record that Hudi-rs fetches from this Hudi table, you can use this to construct your arrow table, which is another data structure. But basically, having the data in a Arrow table makes it super easy to be consumed by downstream libraries or tools that have an integration with Arrow. So DuckDB can consume Arrow, same for Polars, Pandas, or any kind of like Python-based engine that has an integration with that. And we will see this in action in one of our presentation. So as of now, we are in the beginning phases of the project, and of course, would love for the community to get involved and add interesting features, submit any new PRs that they think can be beneficial for Python or Rust users. So we already had two releases, by the way, in this kind of early period of time, which shows the early momentum in the projects and really gives us the drive to bring out these capabilities in this Rust and Python-based workloads. So the very first release, already brings out some nice capabilities that are required as the first steps. I just thought it might be good to see, what we have achieved until this point of time. So of course, Hudi table, two types of table, copy on write, merge on read. With this particular release, we are of course targeting the copy on write table, which is a little bit easier to get started and implement. And of course, we support like two different types of queries. One is the snapshot query that allows you to read the latest snapshot in time based on the latest version of the table. And then there is time travel read, which allows you to go back in time, use a timestamp to query a particular version of the table at that particular timestamp, right? The second is the Rust and Python APIs. Of course, we are using that for retrieving the table schema and reading the tables into our record batch in Arrow. And the third is probably one of the interesting one is the integration with Apache Data Fusion, which is getting Data Fusion is getting a lot of traction in the Spark acceleration space. But basically, it's an extensible query engine written in Rust that uses Arrow as its in-memory format. And we of course have support for this different kind of type of storage schemes in the cloud, AWS, Azure, GCP, that is typically used in this kind of workloads. And in the very latest release, which is the 2.0, we added some more solid features. So one is particularly around like the optimization part. So now it supports partition pruning during file listing. So that means your engine doesn't have to read all of the data residing in all of the partition, and you could basically prune and scan the relevant data files only depending on the partition value, right? So that's a good optimization one as well. We also added a Hudi file group reader class with consolidated APIs to read the record. There was a table builder API for creating table instances, so that is also an interesting one. And we also implemented the Data Fusion's table provider factory that allows Data Fusion users to now register Hudi as an external table and interact with it. So this strong momentum in the early phase of the project is, it's very exciting, and we would love for the community to get involved in any form. So we have listed out a really good contribution guide in the repo by the maintainer. So feel free to read, and there is this particular link that I also put it up. And you can also see the list of some of the very high level, first level kind of issues that anyone who is starting to contribute can pick up. And if you want to make a contribution and be involved in this project, help shape a direction for the project, would really encourage everyone to check the repo and try it out. All right. So now that we understand the goals and fundamentals, how do we use it, right? How do we use Hudi-rs? So like I said, Hudi-rs has both like the Rust API and the Python bindings to read this Hudi table. So if you're in Python, just use pip install Hudi from PyArrow. And if you're in Rust, you can get the cargo or the crate from the crates.io. And once you do that, you're good to read the tables, based on your workloads. All right, so that is basically what we had in terms of like the theoretical part and kind of the high level idea on what is happening in the projects and what's kind of the things planned down the line. Now let's quickly like change a little bit of gear here and talk about like these things in action. So what I basically have prepared is it's a notebook in Jupyter Notebook. I'm going to like increase the size of this. So basically, we're going to just walk over and try to understand how to get started with Hudi-rs, right? So of course, like one thing to like highlight is our documentation, which is already up. If you go to hudi.apache.org, and you can go under docs and find the Python or Rust quick start guide, and it shows you how to install in Python Rust. And also there are like different examples, which really it's super easy take a snippet and get started. And then there is the cloud integration, which we are going to try today. And of course, like things like ability to like read with timestamp. So this will be evolving documentation. And of course, we would like to add more things, more features. And as we do that, this will be updated as well. All right. So now coming here, the first step, of course, is to install Hudi. I already have done that, so I don't need to do it again. I'm going to show you the local table that I have on my file system, which is basically I'm using my file system as my data lake, right? So if I go to my particular warehouse, which in this case is this particular folder, this is where I all have all of my Hudi tables. As you can see, I want to read this particular table. And to do that, I'm going to just, import this particular table and just, read it with this particular read snapshot API, right? So let's do that. Once I do that, I can print the record. And as you can see, this is a record batch object. So that means Hudi-rs has now fetched the record from the Hudi tables that was sitting in my local file system, and it has constructed into the record batch. So the record batch, as you can see, it has the schema and the various fields that are part of this particular data set. Now going to the cloud, which is typically what you would see, being used. This is what I have in my S3 bucket. There's a Hudi table called LinkedIn, and I want to use it for my workload. So let's do that. I hope everything is configured. Yeah. Okay. Perfect. I'm going to use the same read snapshot API here, and I'm going to put the record in the record batch. I did run it a couple minutes before, so I think we should be good in terms of the execution. Of course, here, this is where we can also take advantage of things like partition pruning and stuff that I talked about. But yeah, we can try it out later. So this is what I have, again, the record batch. This is where I have my schema, my entire records, my data set based on my LinkedIn table, right? Now, coming back to the compute part, right? So of course, I have the data as my record batch. Now I want to use a different compute. And I talked about how Arrow helps here. And, once you have an Arrow table, you can then use it for your different use cases. So what I'm basically doing here is basically using PyArrow as the compute, which is PyArrow is a Python API binding for Arrow. And I'm basically using the from batches function to read the record from the record batches and construct an Arrow table, which would allow me to use different compute engine, right? And here I'm doing some basic filtering. I'm only listing out the three fields values here, right? So let's do that. Once you do that, you can see that it's a PyArrow table object. So that means I can use this object to basically channelize into my downstream task. All right. So one of our first example of compute is the DuckDB compute, right? So DuckDB is, we probably know needs no introduction. It's widely famous, used in single node kind of workloads. Really gives you the performance of a in-memory database, if you may. So just install DuckDB. I'm not going to do it here. Of course, I've done it. You need to establish a connection. And what I'm basically doing is I'm just making the connection execute this particular query based on this particular Arrow table that I kind of constructed. So once you do that, there are some dependencies which you can install later. I'm going to just walk through this. And if I now run a select star here, I can see my table with all the information that I wanted, right? Which is great. Similarly, we have Polars. Polars is another compute engine widely used in the Python space. It has features like lazy evaluation, which could be beneficial, for certain workloads and use cases. So you can just install Polars. Polars already has an API to read from an Arrow table, which is the from Arrow method. So once you do that, let me just quickly run it here. You can see it as a Polars data frame as well, and do your evaluation on top of that. And remember, once you bring it to their own data frame in Polars, you can then bring out their optimization, their capabilities of that particular compute engine. Similarly, I have something called Daft, which is another compute engine or a Python-based data frame in a more simpler term. And it allows you to go from a single node execution to multi-node execution in distributed settings. And is something has been I've been trying this out recently. So all you need to do is, again, read the same Arrow table. Daft already has the API to do that. And once you do this, you can see everything in our Daft data frame now. Now, the Daft data frame also allows you to do some logical explanation of the query, the planning, and what has happened if any partition pruning took place, both the physical plan and the logical plan. Here it's unoptimized because we don't have any partition pruning here, so that's why it is. But that is pretty much it that you need to do to get Hudi-rs up and running. Now, one example that I particularly show here is like, for example, okay, you have your data on your DuckDB particular table or a PyArrow data frame or a Daft data frame, right? So here is an example of how you can build a downstream application on by using that data set that you kind of directly read from a Lakehouse table format like Hudi using an engine like DuckDB or PyArrow or Daft, right? So I want to build a dashboard that will allow you to like do like kind of a visualization of all the some of the important metrics. So all of this code is kind of made available. I have made them available in a GitHub repo. But what I'm basically trying to do here is I'm using like Daft as my compute engine, and I'm basically reading the tables directly from Hudi, and I'm building my tables with Streamlit because Streamlit has a Python integration. So all you have to do is basically use that particular Daft compute engine to do your aggregations and all those kind of things. So we did some basic aggregations here, some average price by brand type, category, product variety stuff. So that's kind of a basically a way to see like how we can put this in action. All right, so now going back to our presentation, we are almost done and we saw how to get started. So the community response has been really amazing to see and to get started with. Um, we are in a very nascent stage of the project, so we really welcome any kind of community contribution, and I think we are seeing more of Rust and Python based workloads in this different kind of like settings. So I think it would make sense to bring these capabilities that are already super tight, right, in Hudi. Like for example, capabilities like incremental processing, like indexes, concurrency control techniques, which are super robust and specific to like Hudi. That would be amazing to have that eventually in our future writes and plans in the capabilities. These are the blogs I shared. I'll be sure to like leave out the links in the LinkedIn chat, and you can follow through the GitHub example and try it out on your own and let us know what you think about it. But that is pretty much all that I had today. Thank you so much, everyone, for joining me today in today's episode of Lakehouse Chronicles with Hudi. If you have any question on this particular session, I think I forgot to mention, but this is an asynchronous one. So that means we are going to take questions, but only on the LinkedIn chat. And that would allow us to like be more descriptive and stuff. And we'll be sure to get back with your questions answered within a couple of days. I'll see you in the next episode of Lakehouse Chronicles with Hudi. Until then, take care. Bye.